In this video, I want to take some time to walk through the geometry shapes that we have learned. And I'd like to show you a few models. Typically, we work with little models like this one when we are in class. And so I'll show you them today. And it doesn't quite do the same amount of good because you can't hold it. One thing that you can do if you happen to have something like a soft gummy candy or marshmallows and toothpicks at home is you can create these three-dimensional models yourself, so that way you can hold them and rotate them and look at them. If they're little marshmallows, you can even label each of the atoms. I don't have little marshmallows or gummy candy at home or toothpicks, so I can understand if that's not something that's possible. All right, well, let's still walk through, and hopefully a video showing it will help a little bit with the trick of visualizing these structures in our mind's eye. So I'm going to start with the simplest ones and then work our way down. We're going to start with a linear molecular geometry as an example. So our top molecule here is hydrogen cyanide. And if I were to draw that, so we've got everything here in 2 dimensions. And if I was to draw that in 3 dimensions, it would look exactly the same, which is kind of the nice thing about linear molecules. And linear. My bond angles on each of these, on the atom that's central, so it's any atom that has more than one other atom bonded to it, are the atoms that I'm going to care about the bond angle and shape. And so here the hydrogen and the nitrogen are only bonded to the carbon. That's only one atom. So they don't have a molecular shape associated with them. But the carbon has 2 things bonded to it, and they're exactly 180 degrees apart from one another. They're as far as 2 things can get. So the bond angle would be the same no matter which angle I looked at it around the carbon. And here's what this looks like. I'll try to show this as best I can. Where the the white ball is the hydrogen, the black ball is the carbon, and the blue ball is the nitrogen. And you can see we've got 3 bonds from that carbon to that nitrogen. And looking at this, you can see that that nitrogen atom and that hydrogen atom are completely opposite one another. And we get this perfectly straight line. And that is the characteristic of the linear molecular geometry. And I'm saying molecular geometry, and in this case it is a molecular geometry because linear describes the entire molecule because it only has one central atom. But if it had more than one central atom, that would just describe the geometry at the central atom. It wouldn't tell me there wouldn't even be a name for the entire shape of the molecule other than like blob. All right, so here's linear. Now let's look at our next one. This is ozone, actually. And if I'm going to draw this in 3 dimensions, it's also going to look the same, which is nice. So in this case, we have, again, just one central atom, and we're going to be looking at simple cases here. So that's going to be all of our examples. So in this case, I have one lone pair that is distorting that linear geometry around the central oxygen atom. And it's pushing those other 2 atoms closer together because that lone pair takes up space, just like an atom, like the other oxygen atoms do. And so that's going to give us a bond angle that we see between the atoms, because that's what we're going to count here, of something that would be that 360 degrees divided by 3, because I have the 2 oxygen atoms and the 1 lone pair for a total of 3 groups that take up space around that central oxygen atom. So that's going to give us a bond angle of 120. And we call this shape bent. And here's an example. All right, so here I have 3 oxygen atoms. They're all red. Our central oxygen atom, I'm using this little peach-colored shape here to represent that lone pair that takes up space. So I've got my single bonded oxygen to the central oxygen, my double bonded oxygen to my central oxygen, and the lone pair. So these would be possibly linear if it wasn't for this kind of taking up space and distorting my shape from linear to this bent arrangement. I'll try to rotate this around. And so it's 120 degrees. Let's look at another version of bent. So bent is, this is also, this particular shape is sometimes called V-shaped in some textbooks, or bent. But we have two different structures that have the name bent. So this is one of them. But then our next one, our water molecule, is the same. This is another one that, again, looks the same in 3 dimensions, which is always a treat. And it is also bent. But in this case, we have 1 and 2. We have 2 total electron groups in the the molecule. So here, I'm actually taking that ozone molecule and turning it into a water molecule here. So now we've got 2 lone pairs rather than 1 on that central oxygen. And we still have 2 things bonded to it, both with a single bond. In this case, they're hydrogens, these white things right here. And what's happened is this angle between these 2 atoms that are bonded to the central oxygen, that angle has gotten smaller. They've come in closer together because these 2 lone pairs now take up more space than just 1 lone pair would. And so this bond angle here now represents something that's similar to 4 different things taking up space around a central atom. And so that's going to be about, whenever you have 4 things around a central atom, 109.5 degrees. Now, in the case of water, these lone pairs take up a little bit more space and push a little bit more down. And so we actually see that this bond angle gets to be close to about 105 degrees. So that is something that's characteristic of this molecule specifically. And in general, as you're applying this, rather than memorizing a lot of different bond angles for things that have 4 things around a central atom, I typically suggest that you just remember the 109.5 with the asterisk that if you have lone pairs, that they're actually going to be pushed slightly closer together. And if you really wanted to know what that was, you would grow a crystal of this and you would run an X-ray diffraction experiment and figure out exactly where every nucleus was, and then come up with the bond angle, which, you know, not really something we're going to do in our class. So for the purposes of my class, I'm happy with everything that has 4 things around it, whether it be a lone pair or a bonded atom. It's 109.5. Knowing that if it's a lone pair, it'll take up more space than a bonded atom and give you something smaller, like maybe 105. All right, so that's water. Okay. Moving on to ammonia, which I have right here. So in this case, we're finally going to need to start to draw something that utilizes perspective. So nitrogen is bonded to 3 things with 1 lone pair. So just like this water molecule, there'll be 4 things around this central nitrogen right here. So when we draw this, we're going to need to be able to show one of the hydrogens coming out. So here I've made it, and if you look at it, I've got my nitrogen, and I've got my 3 hydrogens, and I have a lone pair here as well, taking up space. And so these would be all in a plane equally spaced 120 degrees apart around a nitrogen, except the lone pair distorts these and pushes them all closer together. I can't really quite move them, but they all come closer together this way. And so that means this bond angle changes. And since again, I have 1, 2, 3, 4 things taking up space around this central nitrogen, that means that I actually have a bond angle that's going to be close to 109.5. That lone pair takes up more space than this hydrogen, and so it's actually more like 107. But I now, if I want to draw this in 3 dimensions, if you're looking at this, I've got to figure out a way that shows this hydrogen here coming out towards you, and this one back here coming back towards me. And I'm going to use wedges and dashes to do that. So I've got my lone pair here up at the top, and I've got one coming out. And then I'll have one that's going out towards you, and I'm going to use a solid wedge for that. And then I have this hydrogen that's kind of headed back towards me. I'm going to use a dashed line for that one. So in general, I wish I was, okay, let's go like this and hold this and also write at the same time. There we go. Sorry, trying to figure this out. So that's kind of an important tool. I'm a terrible artist. And you don't have to be a good artist to do this kind of, to think about and talk about this kind of chemistry. What we kind of have a convention, because many chemists are bad artists, of showing perspective in a way that's kind of formulaic. So that way we all know what we're talking about. And so in general, when we have a filled in wedge like this, it means that whatever's bonded to it is coming out of the plane of the paper. So it's like coming at you when you look at it. And if you see a dashed wedge like this, it means it's going into the plane, away from you. So here's our ammonium. And this geometry around the central atom is called trigonal pyramidal. And that bond angle between our bonded atoms, it's fine to say 109.5, but it's really closer because this lone pair takes up more space. It's really probably more like 107. And that's going to be something that's pretty specific to this nitrogen. If we had a different element in there and different elements bonded to it, it would possibly be different. So that difference away from that 109 will be influenced by the atoms that make up the molecule. Okay, moving along. Next up we have CH2O, which is this one right here. So in this case, we have a carbon double bonded to an oxygen, and then it's bonded to 2 hydrogens. So this carbon has 4 bonds, but it only has 3 things that are actually connected to it. And so instead of it being 109.5, like other things that have 4 groups, it really only has 3. So it's going to spread these out as evenly as possible, which is going to give us a 120 bond angle between these atoms. And so when I draw this, if I'm thinking of it flat, all of these are in the same plane, right? Like if I can, there we go. They're all in the same plane. And so I can draw this flat on my paper. So in 3 dimensions, this looks very similar to what I have drawn for my Lewis structure. But I'm going to try to represent that 120-degree bond angle as well by showing the 3 things evenly spaced apart in my drawing. And this is trigonal planar. And it's trigonal planar again around that central carbon atom right here. All right. All right, now we've got a carbon atom with 4 things. So it's fun because I actually got to use more colors of the modeling kit. So my central atom here is the carbon again, right there. And I have a hydrogen and a chlorine. Let me change this. I changed it up. Let's make this bromine. So white is the hydrogen, green is the chlorine, orange, the little one, is fluorine, and then purple is the bromine. So I have 4 different things bonded to this central carbon atom. And so if I want to draw this, right now in the Lewis structure, it really looks like there is 90-degree angles around that carbon atom. And so this is one that you really have to think about in 3 dimensions. When I draw this in 3 dimensions, I'm going to use that wedge and dash trick again. And if I look at this, if I look at just focus in on 2 of these, it's very clear that this angle right here is not at all 90 degrees. It's bigger than that. I compare it to my water molecule. So it's really similar to that water molecule in terms of a bond angle between my oxygen and my hydrogens in water. And so when I draw this, if you notice that I'm going to try to hold this up as close as I can. If I put the chlorine and the bromine in the same plane, as if I had a plane of paper that I could just come through and slice right here. So they're in the same plane. Then the fluorine is coming out much closer to you. And the oxygen, which you can barely see, which I'll try to make easier, that's all the way back here towards me, right? And so that means that this is coming back towards me with, I would draw with a dashed wedge. And this one that's coming towards you, I would draw with a dark filled in wedge. These 2 are in the same plane, so they're just going to have plain lines. So let's see what that actually looks like. There we go. So here are my 2 that are in the plane. I've got the chlorine on the top and the bromine lower. And now I have coming out at you, the viewer, a fluorine. And coming back towards me is a hydrogen. And so we would draw it like this, and that would represent this kind of arrangement of atoms. We call this geometry tetrahedral because we have 4 things bonded, so tetra means 4. And looking at that bond angle, just like that water and that ammonia molecule, the furthest these things can really get away from each other is 109.5. And because we have 4 things, that's 360 divided by 4. And we don't have a lone pair on that central atom, so there won't be any distortion that makes that bond angle smaller. And so this kind of also demonstrates the importance of really learning Lewis dot structures and considering them in 3 dimensions. If you move on to Chemistry 131, which is our overview of organic and bioinorganic or biochemistry, then you'll spend a lot of time thinking about these 3-dimensional models when you learn about chirality. Chirality is a critical way that our bodies recognize specific molecules and the way that drugs interact with our body. And chirality that you'll see, and again, this is later, is when you have 2 things that are the same. So I have 2 molecules that both have, so you can see it, that look the same, with the same elements bonded to them. And if I put them up to each other, they're perfect mirror images of one another, but I could never overlap them and have them be the same, right? And so this isn't something we're testing. This is a kind of a look forward to how we're going to use this information. So I can never arrange these in a way where they perfectly overlap. And that makes them different. And your body recognizes these as completely different, which is really cool. And so being able to draw these 2D structures and then interpret them into 3-dimensional structures will allow you to learn about chirality later on.